Okay, we've been asked to solve the equation cotangent of x minus pi over 2 plus 1 equals 0. First step in any of these types of equations with trigonometric functions, if possible, get that trig function by itself. So we're going to go ahead and subtract that one off to the other side to give us cotangent of x minus pi over 2 is equal to a negative 1. So what we're going to do here is change the way that it looks a little bit. So we're going to let theta equals that x minus pi over 2. So now we're really just looking at cotangent of theta to equal negative 1. All right, so now that just means we need to find the angles for which our angle theta is going to be equal to negative 1. All right, so cotangent, same as tangent, it's going to be in a negative number in either quadrants 2 or 4. So here are 2 quadrants. So if we have our triangle here, it's going to be our quadrant 2, or we could be down here in quadrant 4. But in either case, what we're going to wind up with is that negative cotangent we're looking for. And if cotangent is negative 1, that just means that we're looking at the adjacent over the opposite side here. So in quadrant 2, the x values are negative, the y values are positive. And in quadrant 4, the x values are positive and the y values are negative. All right, so here's our first angle theta. So with a 1, 1, the little Pythagorean theorem will tell us the other side is going to be square root of 2. That's our hypotenuse. So that's going to happen when theta is going to be 3 pi over 4. All right. Now, that's going to be plus our period for cotangent, which is pi times k, however many times we're going to be utilizing that period. So next up is our quadrant 4 angle here. Reference angle will still be pi over 4, so that's going to give us an optional of theta to equal 7 pi over 4, and again plus that pi k, which is fine. Unfortunately, we've solved this equation for theta, not for x, which was our goal. So now back here, we told our eyes for visualization purposes, theta was going to be equal to x minus pi over 2. So we're just going to undo that substitution. So for the first part here, we've got our x minus pi over 2 to equal 3 pi over 4 plus pi k. Remember, we're always going to add that plus period times k, whether that's pi or 2 pi k, as soon as we get rid of that trig function from our equation. And now we just need to solve for x. So we're going to add that pi over 2 to both sides here. So that tells us x will be equal to, and then 3 pi over 4 plus pi over 2. It's going to give us a grand total of 5 pi over 4. It's still plus pi k. Right, then here for our theta equals 7 pi over 4 plus pi k. X is still going to be minus pi over 2 to replace our theta. And then that's our 7 pi over 4 plus pi k. And we're going to add that pi over 2 over to the other side here to get x is equal to 9 pi over 4 plus pi k. Now these are our general solutions. However, the interval we were given asked us to solve this over the interval from 0 to 2 pi, and not including the 2 pi. As it happens, 9 pi over 4 is too big. It is past our 2 pi, and another reason to get rid of it here is that is precisely pi units away from our 5 pi over 4, so this guy would really not work either way. And even if it did, we could pick up what we were looking for based exclusively on our 5 pi over 4. All right, so let's go back to him. All right, and so if we let our k equal 0, then we know x is just going to be 5 pi over 4 plus 0, which is 5 pi over 4. All right, if k equals 1, then x is equal to 5 pi over 4 plus pi, which would be the common denominator 4 pi over 4, which is 9 pi over 4, which we already discussed is going to be too big, so we can't use him. Now remember, k values can also be negative. So what we're going to do here is we're going to let k equal -1. X is going to be equal to 5 pi over 4 minus pi, which we'll call 4 pi over 4 with our common denominator. So that tells us x is equal to 5 minus 4 is 1 pi over 4. So our solution set for x be that pi over 4 and 5 pi over 4. Here we've been asked to solve the equation 2 cosine of 3 theta plus 1 equals 0. Now the 3 theta may give you a little bit of an irritating pause, just thinking there might be some kind of double angle formula or some sum or difference of angles formula that you may have to use here. But in fact, if you have a single trig function in your equation and that's it, chances are pretty good you're actually not going to have to go through all that additional hassle. First thing we want to really do here is just get the trig function by itself. So we'll go ahead and start off by just moving that one over to the other side to give us 2 cosine 3 theta equals a -1. We're going to go ahead and divide out both sides by 2. Leaves us with cosine of 3 theta equals a -1/2. At this point, you can actually just try to solve for 3 theta rather than theta directly, or you can do a simple substitution to make this a little bit more, we'll call it visually appealing. So if we do that, we'll let, let's go with alpha equal our 3 theta. So that tells us then that cosine of alpha is equal to that -1/2. And so now we just need to figure out where we're going to have our cosine equal to a -1/2. So cosine, remember, is going to be negative in quadrants 2 and 3. All right, so let's go ahead and draw our triangle here in quadrant 2. This may not be to scale, just wanted to get that little disclaimer out of the way. So cosine, remember, is adjacent over hypotenuse, so that's going to be -1 over 2. With a little bit of Pythagorean razzle-dazzle here, you can get that the square root of 3 is our remaining leg. And that is positive since it's in quadrant 2. The y's are positive there. And for our reference angle here, that's going to put us at a equivalent of 60 degrees, or if you prefer, pi over 3. So for the reference angle, we're covered. That means that the total angle here would be 2 pi over 3. And we could play a similar sort of a game here in quadrant 3. We still have a -1 for the x, then we would have a negative square root of 3 for the y. The hypotenuse will still be a positive 2. The reference angle would still be pi over 3. And so that would give us an angle here, going all the way around, of 4 pi over 3. All right, so that tells us our alpha is going to be equal to 2 pi over 3. Now remember, we got rid of the trig function, so that's where we're going to introduce our period, plus 2 pi k, or it's going to be equal to 4 pi over 3 plus 2 pi k. but we did not solve for theta yet. We've only solved for alpha. So what we're going to do is undo that substitution. So instead of alpha, we're going to have 3 theta to equal that 2 pi over 3 plus 2 pi k. We'll go ahead and solve this one all the way through. Now, you can view this as dividing both sides by 3 to get theta by itself. To make this a little bit easier for visualization purposes, I'm going to multiply both sides by a third. And remember to do all parts of both sides, the 2 pi k included. Alright, so the 3's are going to cancel out here on the left side to just leave us with a theta to equal, this will become 2 pi over 9 plus 2 pi k over 3. Now we're going to do the same thing for our second theta here, that 4 pi over 3 plus 2 pi k. So here we'll have 3 theta equals 4 pi over 3 plus 2 pi k. And then we'll multiply both sides by a third. Try to squeeze that 1/3 in wherever we can have a little bit of room so this becomes visually not so crowded. So that gives us theta here is equal to 4 pi over 9 plus 2 pi k over 3. Alright, so now this would be our general solution, but we were also asked to find the solution over the set 0 to 2 pi. Alright, so remember we found theta equals 2 pi over 9 plus 2 pi k over 3, or theta was equal to 4 pi over 9 plus 2 pi k over 3. So we'll start with this first guy here. So we'll let k equal 0. So that gives us theta to equal 2 pi over 9 plus 0, just simply 2 pi over 9. Remember, we want this to be over the interval 0 to 2 pi. So we're good there. Now we'll go with k equals 1. So we have theta equals 2 pi over 9 plus 2 pi over 3. Remember, the k is being substituted for the 1, so we don't have to write anything down there. Alright, so now to change that to a common denominator, we'll multiply both those by 3. So this gives us 2 pi over 9 plus 6 pi over 9 to equal 8 pi over 9, and we're still good to go. So now we'll go with k equaling 2. So we get theta equals 2 pi over 9 plus 2 pi over 3. K was 2, so we'll multiply that guy by 2 here, which will make that 4 pi over 3, which again we're going to multiply top and bottom by 3 to get our common denominators. Or you could just do this on the calculator, that's also fine. So anyway, that gives us 2 pi over 9 plus 12 pi over 9 to equal 14 pi over 9 for a possible theta, and that is still within our 0 to 2 pi range. Now if we were to go with a negative 1 here, that would put us too small. Again, you can verify that on the calculator since space is limited. I'm going to leave that alone here. If we went with 3, let's see, 2 pi would be 18 pi over 9s, and if we had another 6, yeah, that's going to put us to be too big also. So we're done with that first option for theta. Now we'll use the blue ink here to transition to the theta equaling 4 pi over 9 plus 2 pi k over 3. All right, if k equals 0, then theta is just 4 pi over 9, which is good. That's in our wheelhouse for our solution set. If k equals 1, we get theta to equal 4 pi over 9 plus 2 pi over 3. Remember, k is 1, so that's multiplied by 3. Yeah, let's just start that. K equals 1 business all over again. Right, for k equals 1, theta then is going to be 4 pi over 9 plus 2 pi times 1, which is just 2 pi over 3. So we'll multiply top and bottom by 3 again. So that gives us 6 pi over 9. 6 and 4 is 10 pi over 9, which is just fine for our theta also. Then try for k equals 2. Theta is going to be 4 pi over 9 plus, and I'm going to use the work that we did back here to know that's going to be 12 pi over 9. To give us 12 and 4 will be 16 pi's over 9, which still works. For k equals 3, that puts us at slightly too big of a value. So for our final solution for theta, over the interval 0 to 2 pi, it answers of 2 pi over 9, 4 pi over 9, 8 pi over 9, 10 pi over 9, 14 pi over 9, and 16 pi over 9. Put these in increasing order of just value for theta. If you'd rather organize them by their k values, that's also okay. Doesn't matter the order in which you put them as long as they're all in here. The rest to solve the equation 2 phi minus cosine phi equals 0. First thing I'd like you to take a look at here is that we've got a 2 phi for the sine and then a single phi here for the cosine. So that's what we're going to watch out for, something called mixed angles. We've got those two with different coefficients in front of the variable representing the angle. Situations like this are typically less than ideal because it means we're going to have to use a more complicated substitution formula at some point in our solving process. Now, whether that means an angle addition or subtraction formula, perhaps a double angle or half angle, it's just kind of dictated by the problem. Some situations they may have you try to square both sides, but if you're going to try to do that, you need to make sure that both angles inside the trig functions are identical, whether they're both phi, both 2 phi, both 3p over 4, whatever. That's not what we've got here, so that's really going to be something we're going to try to avoid. And about the only thing we've really got an option for is to play around with this sine of 2 phi with a double angle formula. Now, we know that sine of 2 phi is equal to 2 sine phi cosine phi. We still have the cosine phi here. We haven't gotten rid of that guy, and this is still equal to 0. Now, on the face, but that may not have seemed to help a whole lot since we took a single trig function and put it into more than one. But now we've got cosines in both terms, so we can actually factor that out. So a little bit of trig at first to get that double angle formula utilized. But now we're just going to go back to good old-fashioned algebraic manipulation and factor out that cosine of phi. So inside the parentheses, that'll leave us with 2 sine phi minus 1 to be equal to 0. Now we just have two smaller equations to deal with, whether it's the cosine of phi to equal 0 and then the 2 sine phi minus 1 to equal 0. Now if it's cosine of phi that's equal to 0, that's going to be relatively straightforward because cosine is 0 at when phi equals pi over 2. sine phi equals 3 pi over 2. And remember, we've got rid of the trig function, so that's when we're going to introduce our plus 2 pi k. Okay. Now for 2 sine phi minus 1 to equal 0, first we'll go ahead and add that 1 over to the other side. So we have 2 sine phi to equal 1. Then we'll divide out both sides by 2, so we know that sine of phi will have to be equal to 1/2. Right, so now in that case, when sine of phi is equal to 1/2, we want, that means sine to be the positive 1/2. Sine is going to be positive in quadrants 1 and 2. Right, so we'll go ahead and draw our triangles here to help us identify what's going on. Sine, remember, is opposite over hypotenuse. Pythagorean theorem will get us square root of 3 for the remaining side to help us identify this as a 30, 60, 90 triangle. And in fact, this is going to be our 30-degree reference angle, or pi over 6, since we typically use radians here. And that's going to tell us that our triangle in quadrant 2 will also have a similar reference angle of pi over 6. Right, so we have phi is either equal to pi over 6 plus our 2 pi k, or, and in quadrant 2, pi over 6 is our reference angle. So that'll give us 5 pi over 6. Again, plus 2 pi k. Remember, we add the 2 pi k in because we got rid of the trig function at that step and we're solving for the actual angle. Now, let's go ahead and look for our specific solutions now. We were asked to find solutions over the interval from 0. We were asked to find solutions over the interval 0 to 2 pi, including the 0, not including the 2 pi. All right, so if we start with the angles we found in green from the cosine, right, for k equals 0, phi, when k equals 0, phi equals pi over 2, or phi is equal to 3 pi over 2. And if we do k equals 1, we've got phi equals pi over 2 plus 2 pi, or phi equals 3 pi over 2 plus 2 pi. And since we're supposed to stop right at 2 pi, if we add 2 pi to anything that we've got here, those are going to be too big, so those won't work. Same sort of thing is going to happen with k if you try a -1. It'll be then too small. So we will switch over to the angles we found for sine. So we're in blue here, so when k equals 0, if phi either is equal to pi over 6, or phi is equal to 5 pi over 6. That's good news. Those both work. Those both fall in the interval. So now if k is equal to 1, we've got phi equals pi over 6 plus 2 pi, or phi equals 5 pi over 6 plus 2 pi. And again, since the 2 pi is the cutoff, 2 pi plus anything is going to be too big, so we can't use anything there. Right, so for our solution for phi over the interval 0 to 2 pi, we just have 4 answers. We've got pi over 6, pi over 2, 5 pi over 6, and 3 pi over 2. And that takes care of both the general solutions, which were back here, and over here. Specific solutions right there for that interval. So here we're asked to solve the equation 2 tangent of 2 alpha equals secant 2 alpha. Right now on the face of it you'll see these two instances of 2 alpha and possibly be thinking, well, yeah, that's going to be a whole boatload of double angle formulas and this is going to really suck. Okay, I can't really guarantee you're not going to still think this sucks, but in fact you do not need to use a bunch of double angle formulas here. Since these 2 alphas are the same type of angle configuration for both trig functions, it's quite possible, in fact likely, that we are not going to have to use a double angle formula here at all. So what we're going to do first, though, is take and square both sides. This may seem a little unconventional at first, but it has a really great payoff for us here, particularly since tangent and secant are related through a Pythagorean identity. By squaring the left side, we get 4 tangent. By squaring the left side, we get 4 tangent squared 2 alpha. Parentheses here are just for kind of visual aid purposes. Equals, and then on the right side we have a secant squared 2 alpha. Now, having done this, I mentioned previously that tangent squared and secant squared are related through a Pythagorean identity. If you don't have access to it, as long as you can remember that, say, sine squared x plus cosine squared x equals 1, you can actually solve for the other Pythagorean identities based off of this one. So we know that sine squared over cosine squared is going to give us that tangent squared, so we'll just take and divide out both parts of the left side and the right side by cosine squared, and that'll give us tangent squared x plus 1 equals secant squared x. Right now in this case I'd like to substitute out the tangent squared, so we're going to go ahead and then just take our previous identity, subtract off 1 over to the other side, so we know that tangent squared x equals secant squared x minus 1. So in the case that we have here, we'll have 4 times secant squared 2 alpha minus 1 to equal secant squared 2 alpha. It may seem like things have gotten a little bit worse, but now we're down to a single trig function, so that is in fact much more helpful for us. Now let's go ahead and distribute the 4 through to both terms inside the parentheses, so we get 4 secant squared 2 alpha minus 4 to equal secant squared 2 alpha. Now that we've got that 4 distributed, we're going to go ahead and get this thing set equal to 0, so we'll subtract off the secant squared 2 alpha from the right side, so that gives us 3 secant squared 2 alpha minus 4 to equal 0. Right. Now, typically, we don't like solving equations containing a secant, so we're going to work towards getting rid of that. But for right now, we just want to keep playing along like by the rules that we usually do and isolate the trig function. So I'm going to add 4 to both sides. So that gives us 3 secant squared of 2 alpha to equal a positive 4. And then we're going to divide out both sides by 3, so we know that secant squared 2 alpha is equal to 4/3. Right, now, since secant squared is just 1 over cosine squared 2 alpha, then what I can take and do here is raise both sides to the negative 1 power. Basically, all I'm looking to do is flip both sides. Since there's just a single fraction on each side, that allows me to make that happen. The raising to the negative 1 power is the mechanism by which that's going to happen. So we're left with cosine squared of 2 alpha to equal now 3/4 instead of 4/3. Right, now the cosine squared 2 alpha equals 3/4. It's not the best looking situation to find ourselves in, but it's not truly god-awful either. So all we're going to do now is to get cosine, we're just going to take the square root of both sides. So square root of cosine squared 2 alpha is just going to be cosine of 2 alpha to equals. Now, since we took the square root of something with a variable in it, on the other side, we are going to have a plus or minus, because we have to allow for both possibilities. The square root of 3 is just going to stay the same, but I do know the square root of 4 is 2. So now I'm in a situation for cosine of 2 alpha to be equal to positive or negative square root of 3 over 2. Now, if the cosine of 2 alpha is equal to the positive square root of 3 over 2, then that puts us in either quadrant 1 or quadrant 4. Both of those are where cosine is positive. Right? So for a triangle here in quadrant 1, where cosine is adjacent over hypotenuse, so that'll be square root of 3 over 2 with the low side being 1. So that'll tell us our reference angle here is going to be pi over 6. And in quadrant 4, the only difference here is that the opposite value is going, or the opposite side of the triangle is going to be a negative 1 because we're in the negative y range. Reference angle is still pi over 6. Right. So for our angles for 2 alpha, we're going to have pi over 6 plus 2 pi k, or our 2 alpha is going to be equal to, since we're in quadrant 4, that's going to be all the way around the circle here, just about. That becomes 11 pi over 6. Plus our 2 pi k. Now we still need to get the alpha by itself, so I'm going to multiply both sides by 1/2. Remember to do that to all parts of both sides. And we're going to do that for both equations. So we're left with alpha to equal pi over 12 plus pi k, or alpha equals 11 pi over 12 plus pi k. Then we're just going to go through and choose different values for k. So if k equals 0, alpha is going to be pi over 12, or 11 pi over 12. For k equals 1, alpha is going to be our pi over 12 plus pi times k, which was 1. So our common denominator here would be 12. So that'll give us 13 pi over 12. Or we'll have 11 pi over 12 plus, again, pi, which will be 12 pi over 12 to get 11 plus 12 is 23 pi over 12. And if k equals 2, we have our alpha to be pi over 12 plus 2 pi. Now, since we're looking for solutions over the interval from 0 to 2 pi, that's going to be too big. Similarly, if alpha is equal to 11 pi over 12 plus 2 pi, that's also going to be too big. So these guys we do not have to worry about for our specific solution over the interval from 0 to 2 pi. So we've got 4 so far for our answers, but we've only addressed the positive from our cosine of 2 alpha. So now, let's take a look at what happens with the negative. Okay, so we have cosine of 2 alpha was either equal to plus or minus square root of 3 over 2. We've dealt with the plus, so now we got to look at what happens when cosine of 2 alpha is equal to the negative square root of 3 over 2. Right now, with cosine being negative, that tells us we're going to be in quadrants 2 or 3. Right, so we'll go ahead and draw our triangle here. Cosine is adjacent over hypotenuse, so that'll be our square root of 3 over 2. But remember, in quadrant 2, the x values are negative. The y value will be a positive 1 in this instance. And so again, we have ourselves a 30, 60, 90 triangle. That means we've got a reference angle of pi over 6. And so what we're really looking for here is the full angle, which would be 5 pi over 6. And we want to play the same sort of game here in quadrant 3. The only difference here, our y value will be a negative 1. Reference angle is still pi over 6. So our angle here will end up being 7 pi over 6. So that tells us our 2 alpha will be equal to 5 pi over 6 plus 2 pi k. Since we're getting rid of the trig function, that's why we add in the 2 pi k for the period. Or we get 2 alpha to equal 7 pi over 6 plus 2 pi k. Now, we still want to get alpha by itself here, so we're going to multiply through both sides by half. That's going to be for both equations. This gives us alpha equals 5 pi over 12 plus pi k, or alpha equals 7 pi over 12 plus pi k. And now we just choose our values for k. So if k equals 0, we have alpha equals 5 pi over 12 plus 0, but that's just 5 pi over 12. Remember our interval from 0 to 2 pi, so 5 pi over 12 is good. Now we'll go to the other one here. If it's k equals 0, we have 7 pi over 12 plus 0. And 7 pi over 12 is still good in our confines as well. Now we'll go to k equals 1. Alpha equals 5 pi over 12 plus pi times our k value, which is just 1, so I don't really need to put that in there. Common denominator here will be 12. So 5 pi over 12 plus 12 pi over 12 will give us 17 pi over 12. I'll play the same sort of game here with the other option for our alpha. That's our 7 pi over 12. Plus, again, another 12 pi over 12 to get 19 pi over 12. And we'll try k equals 2. So alpha would be equal to 5 pi over 12 plus 2 pi, or alpha will be equal to 7 pi over 12 plus 2 pi, but in both cases, those are going to be bigger than 2 pi, so we are not going to use those. Now similarly, if we tried for k equals -1, what we would have here is 5 pi over 12 minus pi for alpha, or 7 pi over 12 minus pi, but both of those are going to wind up being negative, so we won't use those either. So that gives us our full solution set to be alpha equals pi over 12, 5 pi over 12, 7 pi over 12, 11 pi over 12, 13 pi over 12, 17 pi over 12, 19 pi over 12, and 23 pi over 12, which is a very long solution set for our interval from 0 to 2 pi. And I'll just rewrite the general solution as well. We had alpha as pi over 12 plus pi k, alpha as 11 pi over 12 plus pi k. We also found alpha to be equal to 5 pi over 12 plus pi k, or alpha equals 7 pi over 12 plus pi k. Alright, so there we go. Here's our general solutions boxed in green, and our interval-specific solutions here boxed in blue.